All right, let's talk about something that governs pretty much everything that moves in a curve, from a car taking a corner to our entire planet orbiting the sun, is called centripetal acceleration. And if you've ever felt that weird sideways push when you're in a turning car and wondered, hey, what's actually going on here? Well, you are in exactly the right place. So, to get started, let's just jump right into a little puzzle, one that kind of messes with our everyday intuition. Picture this. You're swinging a ball on a string in a perfect circle over your head. It's moving at a nice constant speed. But then, what happens if that string suddenly snaps? Okay, here's that exact moment. The string breaks. So, what's next for the ball? Does it keep curving for a little while, like it has some kind of circular memory? That's path A. Does it fly straight out, away from the center? That's C. Or does it fly off in a straight line from the point where it was let go? That's path B. Just take a second. What does your gut tell you? And the answer is B. The ball flies off in a perfectly straight line tangent to the circle. Now, that might feel a little weird. I mean, we all know Newton's law, right? An object in motion stays in motion. So why doesn't it keep moving in a circle? Answering that question, well, that's the whole key to understanding centripetal acceleration. To solve this puzzle, we actually need to get super specific about a couple of words we use all the time, velocity and acceleration, because in physics, they mean something very, very precise. So, first up, velocity. You know, in day-to-day life, we use speed and velocity like they're the same thing, but in physics, they're not. Speed is just a number. It's what your speedometer tells you. It's a magnitude. But velocity? Velocity adds direction to that speed. So 60 miles per hour is a speed. 60 miles per hour north, now that's a velocity. And this little distinction, it is absolutely crucial. And that brings us right to acceleration. We usually think of acceleration as just, hitting the gas pedal. But in physics, it's defined as any change in velocity. And since velocity has both speed and direction, you can change it in three ways. You can speed up, you can slow down, or, and this is the big one for us today, you can simply change your direction. So here's the huge takeaway. That ball spinning on the string or a car going around a corner at a perfectly steady speed is always accelerating. I know, it sounds weird. Its speed isn't changing, but its direction is changing every single second. And a change in velocity is, by definition, acceleration. Period. This special kind of acceleration has a name, centripetal acceleration. Centripetal literally means center-seeking. That string was constantly pulling the ball inward, forcing its direction to change. That pull is the cause of the acceleration. The second the string broke, that inward force vanished. No more force, no more acceleration. The ball just carried on in the direction it was already heading at that exact instant. Okay, now let's take this idea and apply it to some situations you might actually find yourself in. Let's forget about the ball and string for a minute and talk about driving. So, picture it. You're driving on a perfectly circular track, holding a steady speed. From a physics point of view, how many key forces do you think are acting on that car to make the turn happen? Turns out there are three. First, you've got gravity, pulling the car down. Second, the road pushes back up. Physicists call this the normal force. It's really just the force that stops the car from sinking into the pavement. But the real hero of the turn is the third force, friction. It's the grip of the tires on the asphalt, and that grip provides the constant inward push that's needed to change the car's direction. Okay, so if the upward force from the road and the downward force of gravity are canceling each other out, what's left? What's the direction of the net force, the overall combined force on that car? It points radially inward, toward the center. The only force that isn't balanced out is that sideways friction, pushing the car toward the middle of the track. This inward net force is exactly what causes that inward centripetal acceleration we've been talking about. No friction, no turn. If you hit a patch of ice, the car goes straight, just like the ball did when the string broke. Let's try another one. You're driving your car, and you go through a dip, a valley that's shaped kind of like the bottom of a circle. Right at the very lowest point of that curve, how do you feel in your seat? Does the seat push up on you with a force that's less than, equal to, or maybe even greater than your normal weight? You totally feel heavier. At that one moment, the car seat isn't just holding up your weight against gravity. It also has to provide an extra upward push to change your direction from going down into the valley to coming up out of it. That extra upward force is the centripetal force, and you feel it as being pressed down into your seat.
So far, we've been describing speed in terms of meters per second. But, when things are actually rotating, there's a much more natural language we can use, a way of thinking that really focuses on the rotation itself.
And this brings up a really cool distinction. We've been talking about linear speed, basically how much ground you cover every second. But for a spinning object, like a merry-go-round, we can also talk about its angular velocity, how fast it's rotating. And here's the key difference. On a spinning ride, your linear speed totally depends on where you sit, but the angular velocity is the same for everyone.
Let's make this super concrete with an example. So we've got Bonnie on the outer edge of a merry-go-round, and Clyde is sitting halfway to the center. The ride is spinning. Who is actually moving faster, covering more ground per second?
It's Bonnie, for sure. Think about it. In the time it takes to do one full rotation, she has to travel the circumference of that huge outer circle. Clyde only has to travel the circumference of his much smaller inner circle. So to cover way more distance in the exact same amount of time, Bonnie has to have a greater linear speed.
Okay, same situation. But now let's talk about their angular velocity. Whose rate of rotation, how many degrees they turn per second, is greater? And this is what's so cool. Their angular velocity is exactly the same. They're on the same spinning platform, so they both complete a full 360-degree rotation in the exact same amount of time. This is why angular velocity is such a handy tool for describing anything that spins.
So let's bring all these ideas home. We started with a pretty simple puzzle about a string and a ball, and it's taken us through velocity, acceleration, and even two different ways to talk about circular motion. And there's a really beautiful symmetry to all of it. Just look at this. This is where it all clicks together so elegantly. On the right, you've got the standard equations for motion in a straight line, and on the left, the equations for rotational motion. Look at them. They're perfect mirrors of each other. The same physical principles are at play, just expressed in a different language, one for lines and one for circles. It's just an incredible peek into how unified the laws of physics really are. So this whole concept, this constant inward pull, this centripetal force, it's absolutely everywhere. It's the friction of tires, it's the tension in a string, but it scales up to the entire cosmos. It's the sun's gravity that provides the centripetal force keeping Earth in orbit. It's what helps hold spinning galaxies together. So the final question I'll leave you with is this. What else in our universe, from the microscopic to the truly magnificent, is being held in a perfect circle by some kind of invisible inward force? Thanks so much for joining me.